Hello everyone, welcome back to heat transfer. This is Dr. Tian. This class will start chapter 3, static heat conduction. In chapter 4, we'll talk about transient heat conduction. Chapter 6 to 8 will be about convection. At this point, we know that for the special case of one-dimensional heat transfer with no internal energy generation and with constant thermal conductivity, we can calculate the heat rate through this wall as Ka T1 minus T2 over L. Let's rearrange this as T1 minus T2 over L over Ka. We notice there's an analogy between the diffusion of heat and electrical charge. Just as an electrical resistance is associated with the conduction of electricity, a thermal resistance may be associated with the conduction of heat. Here we have this electric current flow I and electric resistance Re. So we have voltage drop across the resistance. And I is the ratio of the voltage potential difference to the electric resistance. We know voltage potential difference is the driving force for electric current. Similarly, we also want to define our thermal resistance as the ratio of the driving potential to the corresponding transfer rate, corresponding to the electric current flow I. In heat transfer, we have the heat rate Q, corresponding to the voltage difference in conduction of electricity, we have T1 minus T2, which is the driving force for heat transfer. In electricity, we have the electric resistance as the ratio of the driving potential to the transfer rate I. In heat transfer, we define conduction resistance as the ratio of the driving force temperature difference divided by the transfer rate Q dot. And from here, we can write T1 minus T2 over Q dot is L over Ka. So the conduction resistance of a plane wall is L over Ka. Similar to electric resistance, thermal resistance also represents this resistive effect of the wall against the heat conduction. For convection, we can use Newton's law of cooling to determine convection heat transfer rate. Similarly, we can define convection resistance as the ratio of the driving potential temperature difference by heat transfer rate. So our convection is Ts minus T infinity divided by the convection heat transfer rate. So it is 1 over HAS. To understand the physical meaning of convection resistance, let's consider convection heat transfer from this wall. We know temperature of the fluid T infinity is unlikely to be Ts, but it's lower than Ts. It's like there's a resistance between the surface and the fluid that resists heat to flow freely in between. So whenever there's a resistance, there's temperature drop. When this heat transfer coefficient is very large, say at the limit of infinity, the convection resistance becomes 0. That is, when convection is really strong, the surface offers no resistance to convection and does not slow down the heat transfer process. Then T infinity would approach Ts. As for radiation, in chapter 1, we derived the net rate of radiation between a surface of emissivity alpha and area As at temperature Ts and the surrounding surfaces at some average temperature T surroundings, as expressed as, note this is sigma, the Stefan-Boltzmann constant. Now let's use the FOIL method to rewrite this term. So it is Ts squared plus T surroundings squared multiplied by Ts squared minus T surroundings squared. Then let's use the FOIL method again on this term. So this term is Ts plus T surroundings multiplied by Ts minus T surroundings. Now let's define the radiation heat transfer coefficient, HR, as the combination of this. So radiation resistance is 1 over HRA. So with the definition of radiation heat transfer coefficient, HR, now the radiation resistance looks similar to convection resistance. Now let's consider one-dimensional heat transfer through this wall with convection on both sides to fluids at temperatures T∞1 and T∞2. We know under static conditions, we'll have the same heat rate flowing through. And here we have 3 resistances, 2 convection resistances and 1 conduction resistance. With conduction of electricity, we know the electric current flow rate is the ratio of the overall voltage difference to the summation of all resistance. In heat transfer, do we have similar relation like this? Now let's derive it. With convection here, we can use Newton's law of cooling to calculate the convection rate, H1A. For conduction through the wall, we can use Fourier's law to calculate it. For the second convection rate, since we have the same heat rate flow, so let's use Q dot to represent the heat transfer rate. From this equation, we have over H1A. From this one, T1 minus, from this one. Now let's add these 3 equations together. Then T1 and T1 cancel out, T2 and T2 cancel out. Then we'll have so for heat transfer, we have a similar relationship. The overall temperature difference can be expressed as the product of heat rate and the total resistance. Actually, the heat transfer rate can be expressed as the temperature difference between any 2 temperatures and the corresponding resistance in between. For example, we can write Q dot as the ratio of temperature difference T∞1 minus T2 to the resistance in between. Between T∞1 and T2, we have 2 resistances. You know the conduction resistance is L over Ka, or it is T1 minus T∞2 divided by the resistance in between. Conduction resistance of the wall plus the second convection resistance. Or T1 minus T2 over the all-day resistance in between. In practice, we often encounter plane wall that consists of multiple layers of different materials. For multi-layer plane walls, we can still use the equivalent thermal circuit theory. For this case, we have 4 resistances in series. We have 2 conduction resistances and 2 convection resistances. The total resistance is the summation of the 4 resistances. And we can express the heat rate as the ratio of the overall temperature difference T∞1 minus T∞2 by the total resistance in between. Or we can express this heat rate by temperature difference between any 2 temperatures divided by the resistance in between. For example, this is also equal to T∞1 minus T1 over 1 over H1A. Or T2 minus T3 over L2 over K2A. Or T1 minus T infinity 2 divided by the resistance in between, which is the summation of these three resistances. With composite systems, it is often convenient to work with an overall heat transfer coefficient U. In industry, we often call it the U factor. It is defined as 1 over our total resistance, A. Note, the overall heat transfer coefficient is always related to the total thermal resistance instead of any individual resistance. For this case, it is. So now we can express the heat transfer rate like this. U multiplied by A multiplied by the overall temperature difference. This is analogous to Newton's law of cooling. Up to this point, we have been assuming perfect contact at the interface of two layers. In reality, if we examine this interface, we can always see lots of gaps filled with air. We know the thermal conductivity of air is a lot smaller than solids. So this imperfect contact introduces some actual resistance to heat transfer. And its resistance for a unit interface area is called the thermal contact resistance. Even though we have developed theories for predicting the values of contact resistance, the most reliable results are still those that we obtained from experiments. Here, this quantity Hc, which corresponds to the convection heat transfer coefficient, is called the thermal contact conductance. Normally, thermal contact conductance is reported in the literature instead of thermal contact resistance. So thermal contact resistance is the inverse of thermal contact conductance. Pay attention to the unit of thermal contact resistance. So this is different from the unit of regular resistance by this. Since thermal contact resistance is defined per unit interface area. Whenever we analyze the heat transfer in a medium consisting of two layers, we need to ask this question. Is the contact resistance significant? Does it make sense to ignore it? To answer this question, we need to compare the magnitudes of the thermal resistance of the layers with typical values of thermal contact resistance. So normally, thermal contact resistance falls in this range. Now let's calculate the thermal resistance of a 1 centimeter thick of insulating material with typical thermal conductivity of 0.04. So its resistance is at this magnitude. Now let's calculate the thermal resistance of 1 centimeter thick of copper. Thickness divided by conduction resistance. And this is the magnitude. Apparently, the magnitude of thermal resistance in copper is comparable to contact resistance. So with copper, we may not want to ignore contact resistance. Here we conclude the thermal contact resistance is significant and may even dominate the heat transfer for good heat conductors, such as metals, but can be disregarded for poor heat conductors, such as insulations. The value of thermal contact resistance depends on surface roughness, material properties, temperature and pressure at the interface, which type of fluid trapped at the interface. To reduce thermal contact resistance, we could reduce the air in the gaps by a thermal grease such as silicon oil, or a better conducting gas such as helium or hydrogen. From this table, we can see the contact conductance of helium, hydrogen, and silicon oil are much larger than that of air. We could also add a soft metallic foil such as tin, silver, copper at the interface. This figure shows the effect of metallic coatings on thermal contact conductance. We can see thermal contact conductance increases with coatings. This figure also shows the contact conductance increases with increased pressure. So we could also reduce thermal contact resistance by increasing pressure between the two layers to enhance the contact. Similar to electric resistance networks, we have generalized thermal resistance networks. Here we have two resistances in parallel. The heat rate Q is divided into Q1 and Q2. So Q is the summation of Q1 and Q2. Note, in a parallel circuit, the temperature difference is the same across each resistance. And we can find the total resistance with this formula. 1 over R1 plus 1 over R2. And it's equal to R1, R2 divided by R1 plus R2. Please recall the total resistance of a parallel circuit. It is not the summation of individual resistance. In this case, we have these two resistances in parallel, and it's in series with this third resistance and the convection resistance. So the total resistance is R1, R2 divided by R1 plus R2 plus R3 plus the convection resistance. In engineering, we often encounter heat transfer in a cylindrical pipe or a spherical shell. Now let's derive the conduction resistance in a cylinder layer or a spherical layer. Let's consider heat transfer in this cylindrical pipe. Hot water flows inside, cold air outside. Let's assume the pipe is really long, so we can model heat transfer in this case as one-dimensional. That is, we only consider temperature change in the radial direction. Let's pick a differential element at radius r. Then we can use Fourier's law to calculate the conduction rate through the surface. That is, Q is negative Ka dt dr. Now let's move A and dr to the left-hand side of the equation. I'll just use Q dot to represent this Q conduction cylinder. Here's a question for you. What is A? Is it pi r squared? Remember, we are calculating conduction rate across this surface by Fourier's law. The area should be the area of the surface which is perpendicular to heat transfer. So A is 2 pi r L. Now let's integrate both sides of the equation. R goes from R1 to R2. Temperature goes from T1 to T2. So at inner surface R1, temperature is T1. At outer surface R2, temperature is T2. Now let's integrate. On the left-hand side of the equation, let's take out the constants first. Q dot over 2 pi L. So within this integral, we have dr over r. The integral of dr over r is the natural log of r2 over r1. On the right-hand side of the equation, let's take negative k out of the integral. Then within the integral, we only have dt. So it is t2 minus t1, or k multiplied by t1 minus t2. So Q is 2 pi k L T1 minus T2 over log R2 over R1. Now we are ready to write the conduction resistance. Remember, thermal resistance is always the driving potential divided by the heat transfer rate. So the conduction resistance of this cylinder is log R2 over R1 divided by 2 pi KL. In words, it is the natural log of outer radius divided by inner radius. Divided by 2 pi by the length of the pipe by thermal conductivity of the pipe. Similarly, we can derive the conduction resistance of a spherical layer. It is R2 minus R1 divided by 4 pi R1 R2 K. Now let's go back to the original problem. We have this cylindrical pipe, hot water inside, cold air outside. So the total resistance is the summation of these three resistances. The first convection resistance is 1 over H1 A1. The conduction resistance is log R2 over R1 divided by 2 pi KL. The second convection resistance is 1 over H2 A2. So now I have a question for you again. What is this A1? Is A1 pi R1 squared? A2 pi R2 squared? Not really. You know, this is convection. The A1 and A2 should be the area of the surfaces which are exposed to convection. So A1 should be 2 pi R1L, and A2 is 2 pi R2L. If this was a spherical layer, the total resistance is the summation of the three resistances. The first convection resistance is 1 over H1 A1. The conduction resistance is R2 minus R1 divided by 4 pi R1 R2 K. The second convection resistance is 1 over H2 A2. So what is A1? What is A2? Remember, it should be the area of the surface which is exposed to convection. So A1 is 4 pi R1 squared. A2 is 4 pi R2 squared. Now let's look at an example. A thin electrical heater is wrapped around the outer surface of a cylindrical tube. So this is the heater. A thin electrical heater. If the question does not further suggest the thickness of the heater, it means we can ignore the conduction resistance in the heater. Temperature at the inner surface is provided. The size of the tube is provided. Conductivity given. The thermal contact resistance between the heater and the outer surface is provided. Apparently for this case, we did not assume the contact between the heater and the outer surface of the tube as perfect. And it is given by per unit length. So pay attention to the unit here. The outer surface is exposed to fluid with known convection coefficient and temperature. So we want to determine how much power is required per unit length from the heater to maintain the heater at a temperature of 25 degrees Celsius. So first, we want to draw the thermal circuit. So how many resistances do we have between the given two temperatures? So we have 5 degrees Celsius here, we have negative 10 degrees Celsius here. So we know between these two temperatures, we have 3 resistances. They're the conduction resistance in the wall, contact resistance between the tube and the heater, and we have a convection resistance here. Let's draw the 3 resistances first. So starting from Ti at this surface, first we have conduction resistance in the tube. Then between the tube and the heater, there's a contact resistance, the Ti here. First, we have this conduction resistance in the tube. This is a cylindrical wall, so the conduction resistance is log Rho over Ri divided by 2 pi Kl. Then we have this contact resistance. Then we reach temperature of the heater T0. Between T0 and T infinity, we have a convection resistance. Convection resistance 1 over HA. This A is 2 pi R L. Next question. What is the relation of these resistances? Are they in parallel or series? To answer this question, we should look at the direction of heat flow. To identify the location of heat flow, first we want to check the location of the heating source. So apparently the heater is this heating source. So we look at the direction of heat flow. We know some of the heat from the heater should move outside and reach T infinity. So this is the convection resistance. And the rest of the heat will move inside, going through this contact resistance and the conduction resistance. So we actually have resistances in parallel here. So we have Q out of this heater. And this heat is divided into 2 parts. One part goes outside, going through this convection resistance. The other part goes inside, going through these 2 resistance. To help you understand this thermal circuit, now I'll draw it in another way which you might be more familiar with. So the heater is at temperature T0. For all the heat out of this heater, it is divided into 2 parts. One part goes to the convection resistance and reaches T infinity. This is 1 over H 2 pi RL. The other part goes to the contact resistance and the conduction resistance and reaches Ti. Since Q1 and Q2 are parallel, so Q is the summation of Q1 and Q2. So now I have another question for you. This contact resistance and this conduction resistance, they're in series. So the total resistance of these 2 is the summation of these 2. The question is, contact resistance is given as 0.01. Conduction resistance can be calculated like this. The question is it correct to simply add these 2 values together? Pay attention here. You should not add these 2 values together because the unit is not consistent. The unit of the contact resistance here is meter Kelvin per watt. What is the unit of this? Remember, this is regular resistance. It is temperature difference divided by Q. So the unit of this is Kelvin per watt. The unit of this is Kelvin per watt. If we want to add them together, we need to make sure the units are consistent. Since this is resistance per unit length, so this should be per unit length too. If we just remove this L, this is the conduction resistance of the cylindrical pipe per unit length. And this is the convection resistance of the pipe per unit length. So now Q1 is T naught minus Ti divided by R contact resistance plus log Ro over Ri divided by 2 pi k. Q2 is T naught minus T infinity divided by 1 over H 2 pi Ro. Plug this back to the equation, we can find Q dot.